Algebra 1, this is all about literal equations. We're right in the middle of Module 2. I think this is topic 1, lesson 3. Sorry about that. We're going to run through some different scenarios where basically we're manipulating equations, trying to solve for different variables in an equation. So let's jump into it. The first question is talking about shoe sizes and an equation that basically uses the length of the foot to also calculate the shoe size in men's wear. So number 1 says the average man's foot is 1.5 inches long. This is an input into this equation here. We have to read closely about which one is which. So it says where F represents the length. So that is where I want to plug that in. So what you see in A down here is me replacing F with 11.5. And as I work that out, 3 times 11.5 is 34.5. Let's subtract that to the other side, and eventually, once we divide by -1, we get that size to be 10.5. Now the second question, part B, wants us to use that same function but determine the x and y intercepts. So x and y intercepts are when the opposite letter is 0. So if you want to find what the shoe size is for a 0 length foot, we're going to plug in 0 for F, and we end up getting -24. Now if you think about that, that can't really be possible. You can't have a foot that's negative in length, and you can't have a negative shoe size, but sometimes the equation has to have somewhere to start so that it can eventually work for other possible shoe sizes. Same thing for the other one. If we were to plug in a 0 for the size, it would tell us what the length of the foot would be, so that would be 80. And so that gives us our intercept points. The next part really wants us to basically tell what the slope and the y-intercept are. So we have to solve out of that equation, and I try to get s by itself here. So I subtracted 3f to the other side. I divided by -1, and you end up getting that the shoe size is equal to 3 foot lengths minus 24. So that slope of 3 and that -24, those represent our slope and our y-intercept in the equation. Number 2 is dealing with volume. You do a lot more with volume when you get into geometry, when you get into Algebra 2 and pre-calculus and a lot of engineering classes. So it says the boxes that shoes come in are often in other capacities once the shopper has bought them. And so the first one says write the equation to solve for the volume of a shoebox. Well, any type of prism like I've drawn over here in this top right corner, length times width times height is how you calculate volume. Now it could also be that you already knew the the area of the base. So if you knew the length times the width part, just the length times the width, you could say it's the base of the bottom of the prism times the overall height, but that's really not a new formula. That's just combining 2 of them and thinking of that being a 2-dimensional area space. So part B says if the area is 112 and the height is 3.5, what is the volume of the box? So they've kind of already told you that the length times the width is 112. That's what they mean by the base area of the box is 112, kind of what I've sketched over here in green. And so we could just say, well, the length times the width gives us the base area of 112. Let's then multiply that by 3.5, and that tells us the volume in that scenario of 392. Now, units are important to understand. Area is in square units because it's a 2-dimensional idea, length and width. But when you went to volume, you have a 3-dimensional space. That's why up here in the top corner I wrote 3D in blue, because you have length, width, and height. And so in this multiplication step in part B, you had square inches multiplying times another set of inches, and those actually add to be a new power. Just like x squared times x would be x to the 3rd. Same concept here. You are adding to the dimension level here. And so we have to say that that's not in inches, that is in cubic inches. So that doesn't mean you cube 392, it just that inches cubed tells you that that represents volume. It represents 3-dimensional ideas. Part C says rewrite the equation and solve for width. So if I'm trying to get the width by itself, let's go ahead and divide the length and the height away And that's what we get for our equation that's solved for width. Part D, a box has a volume of 456 with a length of 1 and a height of 4, and determine the width. So what you've seen me do here is I've started with the volume formula, and I've plugged in that we knew the length was 1, and we knew that the height was 4. And so 1 times 4, if you just go ahead and use the commutative property here to just rearrange those where they're next to each other, 1 times 4, ultimately this is just giving you 4w. Well, let's just divide that 4 away to get w by itself, and that ends up giving you 114 inches. That's what the width would have to be so that you get a correct volume of 456. So question 3 really is just giving us some good practice on how to solve for certain variables in different scenarios. So they're all multivariable equations, which means you have more than just x in there, or more than just y, or more than just a. It's got multiple variables in there. And so in part A, it wants us to basically try to get the big B by itself. So what you see me do is I start with the idea that this is dividing by 3. Let's go ahead and multiply by 3 to get that to the other side. And then if I want h by itself, we can just divide it over. And so in 2 steps, you now have the base by itself. B, this is actually an interest formula. Interest equals the principal amount times the rate over time, all multiplied together. And so similar to volume there, if these are all multiplying and you're trying to get r by itself, we can just divide the other 2 values over. So basically the interest divided by the principal and time would tell you the rate. Part C, x plus y over 3 equals 6. So that's what I did over here on the far right of the board. Let's start by, if it's dividing by 3, let's multiply by 3 to cancel that out. That gives me a new number on the right, 18. And then I subtract x to the other side. And there's 2 possible ways you could write this. You could either say y equals 18 minus x, or you could say negative x plus 18. This is a more common form in Algebra 1 because it follows that slope-intercept form, or the general form of a line. But they're both correct. The last one, this is really talking about in any triangle there has to be 180 total degrees. Let's see, 80 plus 15 would be 95, and then we need to add another 85 there to make a total of 100 degrees, 180 total degrees. Okay? So anytime you have a triangle, the 3 angles always add up to be 180. So if you were unsure about one of them, let's say you didn't know this particular one, but you knew that the other 2 were 80 and 85, well, if they're all supposed to add to be 180, we could subtract the other 2 to figure out that that other angle is in fact 15 degrees. So that's the same thing here, except we don't know what the values are specifically. It's in equation form, so it has more variables in it. And so I'm going to subtract A, subtract B, because you're eventually trying to get C by itself with all of the other ideas on the other side of the equation. Let's jump into a little harder one. This is talking about a pendulum. A pendulum is something that swings from a rope, and so gravity makes it go forward and back, forward and back. And this one's actually on a long string. Has a small metal sphere on the bottom, giving it weight so that it will actually swing back and forth. So the period of oscillation, that's the idea of how long it takes to go forward and back one time, is found by this formula. G is the acceleration due to gravity, L is the length of the string, solve for G. So that seems pretty complicated. It's got a lot of physics concepts in there like acceleration, gravity, but let's just kind of look at that equation and see how we can undo it where you can get G completely alone. So the first thing I start with is 2 pi. 2 pi is multiplying against the radical, so I divide 2 pi to the other side. Well, the opposite of something square rooted, and that I'll show you the step that I did there. Once you divide 2 pi over to the other side, I'm trying to undo the square root symbol. The opposite of adding is subtracting, the opposite of multiplying is dividing, but the opposite of square rooting something is squaring. So for example, if I said, what is the square root of 25? Hopefully you would say 5. But if I said, well, what's 5 squared, you'd be right back to 25. And so they've kind of undone each other, and that's why these operations are inverses or opposites. So what you see me do is I square both sides. We're going to go over here now to the top right side. And so basically when I square a square root, the square and the square root kind of cancel, and you're left with whatever is under that square root, which in this case is just L over G. Now this is a pretty slick part of it, and this can make it a lot easier. But if you don't know this, this problem kind of gets a little harder right here. I'm really trying to get G by itself, and having G in the denominator is a problem. So I'm trying to see how can I get it into the numerator. So what you see me do is I actually do the reciprocal, where I put G and L in the opposite ideas for the fraction, reciprocating them. But if you do that, you have to do that to the other side to keep it fair. So that's what I did. And once I have L in the denominator, I just multiplied it to the other side, and then that finalizes the problem. Let's look at some review. So this problem is talking about a restaurant where the manager is considering changing the prices of how they charge for shrimp. The cost of shrimp is modeled by 50 cents per shrimp eaten. And so the manager decides to change the cost where it's only 25 cents per shrimp, but he wants to go ahead and charge $5 for drinks. And I'm assuming that drinks are required in this scenario. So let's jump into the first part. It says sketch the graph of C of X and P of X. Well, honestly, I kind of had to do part D first. D says write the equation for the function in general form. So instead of there being a rate of change of 50 cents, my new slope is 25 cents. That actually makes it kind of cheaper in a sense. But at first, you have to pay $5 to start. That's kind of your y-intercept here. And so I really needed to do that to begin building the table. So then I start saying, okay, if you don't buy any shrimp, but you're there drinking a soft drink, you're going to pay $5. If you're paying 10, you're eating 10 shrimp and each of them are a quarter, 10 times 25 cents would be $2.50 plus the $5 drink, $7.50. And so once I had this equation, I could set up my table here, and then I could consider graphing it. So this is just a sketch, but basically the green line is where we started. That's C of X. The green line represents just charging 50 cents per shrimp purchased. But the red line actually represents the new one, where they're actually charging less. That 25 cents per shrimp is changed the rate of change to be much less steep than it was for the first situation. That's because you're paying less per shrimp. But you do start a little higher. You have to start at 5 instead of 0. So there is a moment in time where there is a specific amount that you could order where it would not matter. They would end up costing the same. And so that's really not what this question's asking about, but that's definitely where we're going eventually. So now it says, write an equation for P of X in terms of C of X and describe that transformation. So I'll really just focus on the transformation part here. The factor of 1/2, because you basically half the price, and then you've shifted it up $5 because of the $5 drink cost. So if I was going to say, how do I represent P of X? I would say, well, P of X would equal half of C of X plus 5. The next part wants us to solve an equation and then also see if we can determine how many solutions there are. So if you need to pause the video to check that out, I have gone ahead and distributed and combined like terms to eventually get that x equals 3 for number 2. And for number 3, when you distribute and you begin solving, what you notice is eventually the two x's are the same on both sides, and they will eventually cancel out, leaving you just constants, which in this case are not the same, which means you have no real solution. The last one I'm going to talk about real quick is the table that I'm trying to write an equation for. First thing I did was really study the rate of change to verify that it was linear. It does change at the end, it adds 6, but on the same note it adds 3, and 6 divides by 3 to be 2.